Can you hear me, Livy?
Yes, sir.
No problem, right? Okay. Today we'll continue with the game theory. Okay. So I uploaded several more slides there in Lentera. Can you check? So in Lentera we have, I added several slides on network externality system direction control, and then I updated with assignment, and I put a lot of queuing theory slides. Okay, so okay, and you haven't done your assignment yet. I will minus per day. Okay, so okay, let's come to the this is review of last meeting. We have discussed about a dominant strategy, right? I hope you still remember this. Dominant strategy for game theory, okay, is a strategy that gives you a higher payoff. Okay, it's a strategy that give you a higher payoff than all of your other strategy, regardless of what your opponent does. Okay, so the reverse of the dominant strategy, let's call this a strictly stupid strategy. That is a strategy that gives you a lower payoff than at least one of your other strategy, regardless of what your opponent does. So, of course, you will never play this. Right? So, this is the repeat of review of last meeting. Again, how to take the iterative domination algorithm is to take turn, okay, to be at each player's shoes until you found a single cell. So say you play first as row, that means you will look at the first number in any of the two rows. Okay, so if any row actually have larger or equal, okay, depending on strictly or not strict, so larger than the other row, okay, then you should delete the dominated row. The same thing after that, you can play as column, and then in this case you will look at the second number of any two columns, and then you will delete the dominated columns. Okay, so I give example here last time. So now if you look at this payoff matrix, okay, and you play as miss row, okay, that means you will check the first number. Okay. Now let's compare B and C. 2 compared to 1, 1 compared to 0, 0 compared to -1. So that means C is always lower, right? So we delete C. Yeah. Okay. And then now compare A and B. Again, 1 and 2 compare, 0 and 1, and then 2 and 0. So this is not dominated, because 2 is larger than 0. Here is 0 is less than 1. So in that case, you cannot select among A and B. After that, you already deleted C. Let me do this with a pen. So, right? And then now you compare column. If you compare column, you check the second numbers here. So suppose you compare E and F, what will happen? Oops. If you compare E and F, 2 is larger than 1, 1 is larger than 0, but 0 is not larger than 1. Right? How about T and E? 1 is less than 2, this is not. So how about T and F? 1 and 1 is the same, 2 and 0 is larger T, and then 0, so we cannot compare. Right? So we already deleted that. Now, if you look at this, okay, will you play F in this case? 2 is larger than 1, 1 is larger than 0, correct? Right, so in that case, E is larger than F. So again, we delete the F, right? Okay, so now this is our payoff matrix. Is there any domination here? None. Oh, yes, this one. 1 and 2, 0 and 1, right, in the row. So in that case, I deleted this one. And then, of course, now, the last one I deleted that. So this is the last result, which is 2, 2. Okay? So you can some payoff matrix you can do iterative domination until you get the single cell. So of course that single cell means this is the equilibrium. Okay. So up to here, is there any question about this technique to find the equilibrium? Livy, is it okay? Where is he?
Yes, sir.
Oh, I cannot see you. Okay, so let's skip this one. Can you try Pearson's dilemma? Can you find the equilibrium using iterative domination? Anyone want to explain? Anyone want to explain this? How you will get the equilibrium here? Yeah. Okay, you play as Miss Row, and then you. So it will select confess, right? So let's do that. So we will put the pen, -1 and 0, -10 and -8. So this is clearly dominated, right? And then now you compare the column. Okay. Column means you check the second number. So which one is the between -10 and -8? Still confess. So you delete this one. Okay. So this is the equilibrium. So confess is the equilibrium of prisoner dilemma. And you may notice this doesn't make sense, right? Okay, because this is not Pareto optimal. So the Pareto optimality must be T99. Okay. So, and this is what happened. Later we will discuss more detail. This is if you want to generalize. Okay? That actually the value of prisoner dilemma can be any value. Okay? This is the condition for making it as prisoner dilemma. Either you normalize or not normalize is the same. Remember, this is utility, so you can multiply, you can add with any value, positive value. Okay, so you already did this. What is Pareto optimal? So the outcome of a game is Pareto optimal if there is no other outcome that makes every player at least as well off, or at least one player slightly better off. So that means Pareto optimal outcomes cannot be improved upon without hurting at least one other player. So in our game, okay, so the total largest payoff, that will be the Pareto optimal. In this case, you just sum, okay, and you will get this one is actually the total largest payoff, which is -2. So deny is the Pareto optimal. Okay, but our equilibrium is in confess. So clearly, prisoner dilemma game is not Pareto optimal. Okay. How about this? Can you practice? So, what is the equilibrium, and then what is the Pareto optimality? You can just annotate here. Row has no domination, correct? Okay, so then you go to column. Is there any column domination? 7 compared to 0, 1 compared to 0. Okay, so column will not play high, right? Then let's delete that high. Now you play row again. So 50 to 40, 30 to 25. That's will not play high, right? And then now between the two, now you play column. Will not play medium, right? So you have, this is the equilibrium. Okay, so what is the Pareto optimal? This is 57, that is, the highest is high medium, right? This is the highest, is that correct? So this is supposed to be the Pareto optimal, but the equilibrium is not the same. Okay, so in this game, yes, yeah. So the equilibrium is at this point, okay, and so this is the equilibrium. 57 is the equilibrium, but the Pareto optimality is 85. Okay. Okay, so there is another type. Say, if you cannot find domination, okay, there is another technique which is very well known. You can see the movie Beautiful Mind, and John Nash get Nobel Prize. Okay, so this is the name of the person, Nash. So Nash equilibrium is a state of the game where no player prefer a different action if the current action of the other player are fixed. So you need to fix the action of one player and then you check the other one. Okay. So the definition, yeah, a strategy combination is called Nash equilibrium if no player have incentive to deviate from this strategy, okay, given that the other player also do not deviate. So it's not a equilibrium is not always the best thing, but this is like you are stuck there. Okay, so it's a fixed point. Equilibrium is basically a fixed point, right? It's a constant. In difference equation, this is the constant value. Okay, so the technique, okay, you need to propose a strategy combination as if, okay, one of the player move first. Then you test, okay, whether each player strategy is the best response to the other strategy. Okay. So how to do that? Okay, so this is what I'm trying to do, simplify it, to make it into an algorithm. So first you assume the row, Miss Row will play first. Okay, and then for each strategy of the row, okay, given this strategy is chosen by row, now the column will select the best strategy for column. So, and then put that best strategy for column as list 1. Okay, after that you assume column will play first. Okay, now for each strategy of the column, again, given this strategy chosen by the column, the row will select what will be the best strategy for row. And then let's name this list 2. Okay, and the Nash equilibrium is the intersection of list 1 and list 2. Okay, let's try. Before that, we can also say it's a superior Nash equilibrium, because Nash equilibrium can have several cells. Okay, so now among this best strategy combination, okay, row will select the best strategy, right? That is called superior Nash equilibrium. Okay. The same thing if the column play first, okay, given this strategy by column, the row will select what is the best strategy for the row. Okay, among this best strategy combination, the column will select the best strategy, that is called superior Nash equilibrium for the column. Okay, let's practice, okay, with this example. So this is called the battle of sexes. Okay. So the story behind is something like this. So there is a conflict between a man who wants to go to a soccer game, okay, and his girlfriend who want to go to a ballet. Okay. So while they are selfish, they are also deeply in love, right? So then they also want to sacrifice their preference for each other. Okay. So this is the battle of sexes, battle of love. So let's say we have two players, Miss Row and Mr. Column. Top maybe soccer game, okay, and bottom mean ballet or whatever. Okay, so we have two strategy. I call this top and bottom and left and right. So if Miss Row select top and Mr. Column select left, okay, Miss Row will get 2, right, and then Mr. Column will get 1, okay, and so on. Now let's find the Nash equilibrium for this payoff. So first let's play as Miss Row. That means look at the first number in this case and check if there are any dominant strategy, and you see 2 is larger than 0, 0 is less than 1, so there is no dominant row. And then you check as Mr. Column, right? That means you check the second number, is there any dominant column? Again, you cannot find. Oh no, you cannot solve using domination strategy, okay? So in that case, let's try Nash equilibrium. So again, if you can solve using domination, solve it using domination. Don't use Nash equilibrium. Yeah? So that's the first thing to do. Okay, let's solve this using Nash equilibrium. How to do? Assume first that Miss Rho will play first. Okay, this assumption is crucial. In reality, this is played simultaneously, right? But in computing the Nash equilibrium, you assume, okay, one of the player will play first, not simultaneously. That is the crucial assumption of computation. Okay, so say Miss Rho play first. There are two possibilities. Top and bottom, right? So this is the tree diagram. And then after that, Mr. Column will play either left or right. Okay, and this the outcomes is actually there. I just copy this payoff matrix into this tree. Okay. Now remember, this is Miss Rho play first. Okay. Now, Mr. Column will select what? Yeah. So, if Miss Rho play top, what Mr. Column will select? Can you see? If Miss Rho play top, what Mr. Column will select? Okay. So you look at the second number. I will put the laser pointer here. So suppose Miss Rho play top. Okay. Now you check Mr. Column. That means 1 and 0. Which one Mr. Column will select? Left, right? Because 1 is larger than 0. So then, if top, okay, if Miss Rho select top, Mr. Column will select left. So I put here TL, mean top left. Okay. Now, what happens if Miss Rho select bottom? Okay. If Miss Rho select bottom, what is Mr. Column will do? Check the second number here, 0 and 2, right? So Mr. Column will select right, correct? Yeah, between 0 and 2, 2 is larger. So in that case, the equilibrium will be bottom right. So I put here BR. That means bottom right. Okay, so this is list 1. Now, between TL and BR, okay, now between these two, okay, can you see this one and this one? For Miss Rho, which one is the superior? This is 2, this is 1, right? So in that case, TL is superior compared to BR. Can you see it? Okay, so then the superior Nash equilibrium here is TL, that is top left. Okay, next, the other way around. Okay, let's assume now Mr. Column will play first. Okay, the same payoff matrix. Now we draw different diagrams here. So Mr. Column will play first and then Miss Rho. Okay, so if Mr. Column will play first, left, what Miss Row will do? You look at the first number, right? 2 and 0. So of course, Miss Row will select top, right? So in that case, again, we have top left. Why? The list must be written row column, okay? So that you can intersect, otherwise it's not correct. So again, this is top left, so TL. Now, if Mr. Column select right, what Miss Row will do? Comparing 0 and 1, Miss Row will select bottom. So then again we have a new equilibrium here with this bottom right. So we have TL and BR, right? So now the intersection of list 2 and list 1 a while ago, okay, is again the same, right? So TL and BR. So this is the Nash equilibrium. Yeah? You have two Nash equilibrium. And now, if you compare, okay, between TL and BR for Mr. Column. So this is the TR and BR for Mr. Column. The BR will be the superior. Okay? Do you get it or not? So the battle of sexes have two equilibrium. Yeah? And this two Nash equilibrium is also Pareto optimal. Yeah? Okay, up to here, is there any question? Is it clear? Can you calculate Nash equilibrium or not? You want to practice? Okay. Try first and you practice on your own. Okay, because after this we will repeat doing this. The important point is, if you want to see the equilibrium, that means you will find, okay, what is the strategy of other people, and then you will start to think in their shoes. This is the main lesson in game theory, actually, right? You will start to think in their shoes. Okay? What is their thinking? Then you start to see if they do like that, then what will be your strategy? So that is the technique in game theory, always. And this is very important technique, isn't it? Even in life. So when dealing with anything, so you start to think, okay, this is my point of view. Okay, then you start to think of other people's point of view. Okay? Then you can start to devise your own strategy based on that. As simple as that. Is it clear? Clear, yeah? Livy, clear?
Yes.
Okay. So now, you see in the battle of sexes, okay, there are two Nash equilibrium, right? So if Miss Row or Mr. Column actually announce first, okay, his or her strategy, then the one who announced first will gain advantage. Okay? So this is called the power of disclosing strategy. Information, remember. Those who has reputation of inflexibility and then disclose first will gain the advantage in this game. So you the example, if you can tell like this, I'm going to do this. Make up your mind and do what you want. Okay, then people will start to think their way, even though the game is actually balanced. Okay, something like Battle of Sexes, right? Then they will select what you want. Okay, so if no pre-play communication and the player need to select simultaneously, they may end up in non-equilibrium. So, right? Okay, this is another version of Battle of Sexes. Okay? Uh, the scoring here represent high love or low love, right? So again, the value can be anything. So this is still Battle of Sexes. Yeah? And the one that I put here is actually the Nash equilibrium. Okay? The one a while ago is here. Okay, so this is another game called educational marketing. So a big company spend considerable marketing expenses in educating the public, right? And then the small company then imitate, okay? Just imitate profitably without ruining the big company sales completely. But if the small company introduce them at the same expense, okay, and then an imitating big company will dominate the market. Right? So to educate the market, you need a lot of campaign money. Right? So now there are two companies: small company or big company. If the big company thinking to educate the market, okay, and the small company only imitate, okay, the big company will get 4 and the small company get 4. If the big company educate the market and the small company also joining educate the market, of course the big company win. Okay, so we'll get 5 and small company only get 1. Okay, now if the big company just imitate, while the small company is the one that educate the market, okay, of course the small company losing, -1 here, and the big company will win. Okay? If both are copying each other, so they get 0. So can you find the Nash equilibrium and probably the Pareto optimal of this game? There are 2 Pareto optimal here. That's easy, right? This is 8. This is also 8. So this is Pareto optimality. Can you find the Nash equilibrium? First, you check if there are any domination. Is there any domination? Row dominant? No. How about column? Column domination, there is. 1 and 4, this is lower. Oh yeah, this is educate is clearly dominated, right? So, and then after that you can yeah, correct. Yeah, okay. And after that I cannot get the row. No. I mean, after column, I supposed to do the row, right? But there is no row. So, yeah, if I play as if you play as big company, no dominant, and then if you play as small company, imitate is the dominant strategy. Okay, imitate is the dominant strategy, and then you play as big company. If you play as row, which one is the dominant? This is 4 and 0, right? So in that case, 0 is no more. So this is the Nash equilibrium. Is it correct? That one is educate imitate. Yeah, correct. So using domination, you can already solve this, so you don't need to calculate the Nash equilibrium. Right? So now, if you want to do Nash equilibrium, what you will do? Okay. Let's check if the Nash equilibrium is actually the same as domination. Okay, so say you play as big first. Okay, so in this case you have two possibilities: educate and imitate, and then small company have also two possibilities: small, educate and imitate, and we just copy the outcomes, right, from the here. So if big play first, so what the small will do? You check the second number. So this is dominant. If big play first, what small will do? This is dominant, right? So then we have educate, imitate, and then imitate. Yeah, so I put it here as this one, right? So among these two, which one is dominant? For the big player, educate, imitate have 4, and here is F0, so 4 is winning, right? So in that case, educate, imitate is the superior Nash equilibrium for the big player. And then next, you try to reverse the role. Is small play first. Okay, so if small play first, you draw differently. You will check, okay, if small play educate, what the big company will do. You look at the first number, okay, between 5 and 9, 9 is winning. Okay, and then if small play imitate, what is the big company will do? Between 4 and 0, so 4 is winning, right? So in that case, you have imitate, educate, and then you have again educate, imitate, educate, imitate. So if you take the intersection between the two, again you get educate, imitate, which is the same as domination. Can you do it or not? No problem, right? Yeah. Okay. So you know how to calculate Nash equilibrium. You know how to calculate using domination. You also know how to do to compute the Pareto optimality of a game. Right? So if you calculate Nash equilibrium of Pearson dilemma, will you get the same result of as iterative domination or not? Anyone want to use a whiteboard and then you try? Yeah, Nas equilibrium of a prisoner dilemma. Okay, try to create a whiteboard. Draw. Yeah. Cool. Or you can use I don't know, annotate or I don't know. Maybe you don't need whiteboard. Maybe you what you need is what is that called? Drawing pad. Uh, what is the drawing pad? If you are using Windows, or you can use Excel or Word if you want. That's also fine.
Sir, I can share using my
Yeah.
phone.
Okay, go.
Yeah, okay. Let me share screen then. Yes. Let me, so the question is, I just need to draw the.
Okay. First, you will select as Mr. Row, right?
Yeah.
So
I
you
need
just
to
add.
draw the table or not?
You just draw the tree diagram of say Miss Row is R. Just put
Okay.
okay,
R
and
Q.
then you have deny is D and then C, right? Okay, and then for each of that you have a column, so you can put column. Again, you have deny or confess.
Yes.
Okay, and then you created the leaf for that. It's just
All this.
right.
So
The payoff, you need to put the payoff.
if the row is one,
One,
if the row select D,
the payoff is negative. So if row play first, what the column will do? So that means you look at the second number. it's better if you put the numbers there. So -1, -1.
Okay.
You
This
can
one.
see.
Let me just make it like this. So, this one confess. The column will deny.
Mhm.
This one is for the column.
Yeah, and then put the numbers. So -1, -1.
This one, 99 is negative. Deny confess. And then confess deny.
Deny confess is -10, yeah. The first one is -1, -1.
Oh,
Okay.
yeah.
And then if row select deny, what the column will do?
We'll select confess.
Will select confess. So you can just put under
Oh,
DC, right?
we'll select this one, right?
Yes, correct. And then if row select confess,
If row select confess, the column will select confess.
confess. Yes.
Yeah.
So let's put that as DC and then CC.
DC, CC.
Okay, good. Now you create a second one. Now column play first.
Column play
So you
first.
create another 3.
Oh, okay. So the column.
Yeah. The C. Again, you have deny and confess.
Yes. And
And then now the row. Again, deny and confess. And then again, you put the payoff. Deny, deny is -1. Here is confess, deny. Confess, deny is
confess deny is 0.
0, -10. Okay. Is
What is 1 is
deny, confess. Deny, confess. Okay. And then that is confess, confess. Okay. Now, if column play deny, what row will do?
if column play deny, the row will choose this one.
No.
If column play deny, or
If,
confess.
you
Oh,
need to see the first number in this case. Right? Because column already play deny. Okay? So then you need to see the first number. What row will do? Between -1 and 0, what row will do?
row will choose -1.
Between -1 and 0,
Oh, 1 and 0.
right?
Uh-huh.
In that case,
Oh, confess.
correct, right?
Mm-hmm.
And now, if columns say, I will do confess, what row will do?
Deny.
Hmm?
Huh?
First number. Row will do mean the first number.
Oh, row will confess.
Correct. Between -10 and -8. So
Mm-hmm.
now you need to make a list too. This is where the danger comes from. The list 2 must be also row column. So in that case,
CG.
CD
Yeah, CG.
and CC. Okay, very good. Now, easy. Just get the intersection between the two lists, right?
CC.
Correct, CC. So confess, confess. So this is exactly the same as domination strategy, right?
Yeah.
Okay, excellent. Clear, yeah?
Yes.
Okay, very good. Joy, no problem, right? So we have solved the Nash equilibrium for prisoner dilemma. So you're done. Okay, so right, this is the answer. Oh, can you practice this? Okay, this is interesting. What is the Nash equilibrium of this game? Actually, if you can imagine your tree diagram in the mind, you can solve Nash equilibrium without any calculator, without any drawing, but by look at it, you already know. Okay, first you think, you play as Miss Row, okay, and then Miss Row play first. That means you check Mr. Column. Okay, check the second number. Okay, between C and D, okay, if Miss Row play A, let me use laser pointer. Say, you know first, I will say Miss Row play first A. Okay, what Mr. Column will do? That means 0 and 0. There is no difference, so will not select, right? Now, if Miss Row play B with 0 and 1, so 1 will do, right? So in that case, uh, we'll say, okay, for Miss Row play first, this is the one. Okay. How about Mr. Column? Now, Mr. Column will play C. What Miss Row will do? Cannot decide between 0 and 0. Yeah? And if Mr. Column will play D, what Miss Row will do? Of course, will do this one also, right? So, in that case, that is the equilibrium, right? PT. Okay? Is this okay or not? You can actually find the Nash equilibrium without drawing. You know, you just look at the numbers and then compare. Okay, one by one, then you can actually doing it. Very easy. Right. Okay, matching penny. Okay, the story behind. So each of the two players select either head or tail. If the choice different, okay, the Miss Row will pay Mr. Column $1. If they are the same, Mr. Column will pay Mr. Row $1. Okay, so that is the payoff there. So this is a very strictly competitive game. Okay, can you find the Nash equilibrium here? find the Nash equilibrium in this case. Hmm? So, what is the Nash equilibrium? Yeah. So, if you look at the result, okay, actually list 1 and list 2 are different, right? So the intersection is actually empty, right? So matching pennies has no Nash equilibrium. So this is one of the possibility, okay? You can either have Nash equilibrium or no Nash equilibrium. And if you have Nash equilibrium, not necessarily 1. It can be 2, can be 3, and so on. So this sometimes can be confusing at first. But remember, Nash equilibrium is not unique. This is important. And not necessarily exist. Okay? So this is the example that Nash equilibrium does not exist. Is it clear or not? Okay. How about this one? So this is in real life, okay? So we often say, should we play dove or should we play hawk? Okay. So two animals are fighting over something, right? And then each can behave like dove, meaning peaceful, willing to lose, okay? Or can play as hawk, meaning fighter, always want to win. So of course, each of you can play this way, right? Now you have two players. Either you want to uh, give way to others or no, right? So if you play dove and Mr. Colin also played dove, you are Miss Rowe, okay? And then the two of you will get 3-3. That means this is Pareto optimal, right? But if you play dove and your opponent play hawk, the hawk will win. Okay? You get only 1, and as Miss Rowe and Mr. Column will get 4. The same thing if Miss Rowe play hawk and Mr. Column play dove. Okay, and then if both play hawk, okay, this is will get 0-0. So which one you should play? This is a very nice implication. You know the Pareto optimal is clear in this case, right? Dove. Okay. But what is the Nash equilibrium? Okay, what is that? And octave. Okay, so the way to do fast is something like this. I will, if Miss Rowe play dove, okay, So select between 3 and 4. Of course, we'll select 4. So I will put here 4. Okay. If Miss Row play hop, select between 1 and 0. We'll select 1. Correct? Now, if Mr. Column play dove, okay, what Miss Row will do? Between 3 and 4, select 4. Right? And then if Mr. Column play hop, okay, select the first number between 1 and 0. Again, this one. So that's correct. So this is the 2 NAS equilibrium. Okay. Yeah, correct. Okay, so you see the NAS equilibrium is not Pareto optimal. And this is different from prisoner dilemma, isn't it? Okay. So if you know, okay, if you know the opponent will play certain strategy, then you know what you should do, right? But if you don't know, then there are 2 possibilities of these strategies. This is another game that is also very interesting. Later we will expand this, okay, into one whole slide file. This is called coordination game. Okay. The player will benefit from cooperation. Okay. This is how you will do. So in this case, the player need to coordinate their action. Okay. If the player hide the move or lie about what she is planning to do, she will get penalty. Okay, so if Miss Row play A and Mr. Column play C, okay, both will get positive one. Okay, so if they cooperate, okay, they will get positive one. Now, if they don't cooperate, both will get 0. Okay. So if one cooperate and the other not, so you will get -1 and -1. Okay. And you can see these 2 have this game have 2 NAS equilibrium, the one that I pointed out there. Okay, so this is often the practical application of that coordination game. Okay, so look at this. If you are in the intersection, okay, and both go, right? So accident may happen, right? And then if one stop, the other one go. So the one that go will move, and then the one that stop don't move. Okay? If both stop, both of them don't move. So this is in traffic signal. So basically, traffic signal or in the intersection is coordination game. Okay. The same thing in this situation. If 2 workers demand a raise salary, okay, if both of them demand raise, okay, both will get raise, right? If only one demand raise and the other one is a traitor, don't do anything. So one demand raise get fired, and the other one get nothing. Okay. If they do anything, then of course they get nothing also. So this is coordination game. So look at the situation, then you will know what kind of game is this. We introduce you with various kind of games, right? And we keep names so that easily we can distinguish, and you will know, oh, this is actually hawk and dove game, or this is actually a coordination game, oh, this situation is actually prisoner dilemma game, and so on. Okay. This is called dangerous coordination games. Can you find the mass equilibrium of this? So if Miss Row play A, what Mr. Column will do? C. So let's write that as C. If Miss Row play B, what Mr. Column will do? D. Now, if Mr. Column play C, what Miss Row will do? Okay, so we'll do A. If Mr. Column play D, oh, this is again coordination games, right? So even though the number seems different from the usual coordination game, you know this must be coordinated. Is this clear or not? Vivi, you have any question, feedback?
No.
So far you can do?
Yeah. Only just for the wait the one. If we play with the row, I'm still okay, but the column, I guess. So we still read the value as row, comma, column.
Correct. So in example, okay, I will restart again. Let's play this, okay? In this example, first you play as Miss Row, okay? So if you play as Miss Row, that means you compare the second number, 2 and minus 1. Which one is larger?
2.
2, right? So then you mark here. Can you mark? Okay. So I'll mark it here. Okay. And then now you play Miss Row as B. Okay. Again, if Miss Row already play B, right? Assuming that Miss Row is already play B, what Mr. Column will do? Between minus 1 and 1, right? What? Which one is larger?
1.
1. So we mark here. Okay. Now, this is all right for Miss Row. Now you said, okay, now I play as Mr. Column. Mr. Column said C. Okay. What Miss Row will do? Mr. Column said, I play C. So Miss Row will compare 2 and minus 1, correct? If Mr. Column plays C, okay, it's already here, okay, only in this column, C. Okay. What Miss Row will do? Miss Row will compare 2 and minus 1. So which one is larger? 2 and minus 1. 2, right? So then you write 2 here. Okay. Next, if Mr. Column said D, okay, between what Miss Row will do? Between negative 100 and 1, of course, will do 1. So then these 2 are the actual mass equilibrium. that okay? Oh, she went off. Yeah, we have. Oh, this is another game called Game of Chicken. This is a car race, okay? Uh, it played by choosing a long straight road with white line down the middle and starting two very fast, okay? The car toward each other from opposite end. Okay? Now, if the car expected to keep the wheel in one side of the line, okay? If they approach each other, the mutual distraction will become more and more imminent. Right? So if one of them swerve from the white line before the others, and the other pass, will shout chicken. Okay? So the one who has swerved become the object of contempt. Loser, meaning chicken means loser. So this is the payoff matrix of the game of chicken. Okay? If the two of them continue in the game of chicken, okay, it will become mutual destruction, right? They will have accident. So -3 and -3. If one of them swerve, right? So if Mr. continue and Mr. Column swerve, right? So Mr. win 2/0. Right? But if the two of them swerve, okay, they are put chicken, so we'll get 1 and 1. So what is the Nash equilibrium of this game? Can you try? Yeah, game of chicken. Can you try? What is the Nash equilibrium of the game of chicken? Can you try the game of chicken? Okay. Anyone want to try the same technique? Yeah? 2 equilibrium. Yeah? Which one? Yeah, continue solve and solve continue. That's correct. The Pareto is the three of them. Right? Yes, because 2 plus 0 and this one is also 1 plus 1. Right, this is the game of chicken Nash equilibrium. Oh, this is your assignment. You did not make it, so Oh, you already make it. Very good. Okay, so now, wow, super. So I modify the rock paper scissors. Okay, with this different points. Okay, you can also play by yourself. What is the Nash equilibrium? Okay. Of course, you can play domination, but let's try. What is the Nash equilibrium? Yeah, you can annotate here. Yes. So if you play seesaw, if the Miss Row plays seesaw, what Miss Column will do? Rock. Yeah, why is it gone? You can put under. Put under the number 2 so that you will know. Okay, 3 and then 1, correct. And then the 2 and 3 and oh, there's no Nash equilibrium. Okay, again there is no Nash equilibrium because there is no intersection, right? So this game have no dominant. Okay. Oh, sorry. So also known as equilibrium, but there is a Pareto optima, right? Uh, 3. Yeah? The 3 is a Pareto optima. So known as equilibrium. So the strategy to play this win the game. Yeah? If people know that playing seesaw will always give a Pareto optima, right? As people will try to play seesaw and avoiding paper. So knowing that, then you will play rock as often as possible to win the game. So based on Pareto optimal, you can also devise your strategy of the game. Right? Oh, this is the last exercise. Can you find the Nash equilibrium of this? Okay, so the Nash equilibrium is traceable and traceable. So what is the implication of this game? Right? What is the implication of this game? No, no, no. How are you going to create that everyone must be honest? So basically, you can create a society, okay, or organization, or within the company, or within your family, that everyone will be honest if, look at the payoff. If you put, okay, they are trustable, you give reward much higher than if they lie. Okay? And if they lie, both lie must put very low. So by designing the payoff matrix, okay, by designing the payoff matrix, what is the meaning of payoff matrix here? This is the reward and punishment, isn't it? Okay. So by designing the reward and punishment for each action, you actually can create a better society. Okay. So that's the I put here. Society will be better off if the liars are punished, not encouraged. Okay? The trustable person are rewarded, not punished. So if you ask, is there any, look at the Pareto optimality, also trustable and trustable. So this is very nice game, okay, that will probably awaken something within us, that trustable society is possible. Okay. How to do that? Based on this game theory. Okay. Actually, China start to make this kind of system, isn't it? Right? Using their mobile. Okay, so you can also practice if you want. You can see here there is a real world situation in the intersection that you can see how accident may happen and so on, and you can read, and based on this you can create the payoff matrix and then find the mass equilibrium for this. Okay, the same thing with this different scenario in the, and then you can also find the mass equilibrium. If you need the book, I can share with you in Ventera, but if not, that's fine. You can find by yourself also. Okay, so, okay, give me feedback. What did you learn today? And Pareto optimal, right? So you learn various games, okay? The difference is only the payoff, okay? And I hope by learning this, a few well-known games. This is all from textbooks, so except for the trust game that I created. So okay, so all the others are well-known games in the textbook. Then you can start to think of any situation that you have, and then you can start to use that for your real life. Okay, is there any question? Is there any discussion that you want to talk about this game theory? Livy, any comment? Question?
All good now.
Good.
Yeah.
Okay, so I want to show you some research, okay, in the next slide. Can you check the slide of system control based on game theory? So this is basically the same as a while ago. Okay. My question is, how do we create a system that is controllable based on game theory, right? And I want to point out two in here. It's a prisoner dilemma model and the trust model that we discussed a while ago. And then I will discuss about the principle right direction of control and how you will design the system, okay, to be controllable based on what you want. Okay, so you know, prisoner dilemma game is basically about compete or cooperate. Yeah, deny confess a while ago is actually compete or cooperate, right? So in each time of the game, each of the two players have choice either to cooperate or to compete, right? Again, the assumption here that each player does not know how the other behave and they are not able to communicate. So the problem with the prisoner dilemma is actually lack of trust. Okay? So I give you a real world situation. Okay? In the software development company, we put the situation where both of them, if they cooperate, yeah, say we have two teams, right? If the project completed on time, team A and team B will get a bonus, right? Then their personal contribution is evaluated similarly. Okay? So they will share bonus 50-50. So I put here the value 5 and 5. Yeah? Give you the laser pointer. So you see here, this is the 5 and 5. And then if A cooperate and B compete, okay? So A cooperation will lead to the project completion on time. Okay? The team will get the bonus. However, as A has to dedicate part of development time to understand the complicated code that B make, okay? A personal contribution is evaluated smaller than B. Okay. So say B compete by making the code complicated, okay? And A is cooperating. As the result, B will get 80% of the bonus, while A will get 20% of the bonus because you know the number of code that they create is actually smaller. Okay. So and the same thing, yeah. If A compete, B cooperate, you will get the reverse, 80% for A, and then B is only 20%. Now, if both of them compete, so of course the project failed, and no one got bonus, 0-0. So if you look at the value here, you know this is actually prisoner dilemma game, right? And you also know what is the Nash equilibrium, right? The Nash equilibrium will be compete. Okay, so that means this is the situation where because of your bonus system, okay, yeah, then you create a trouble for your own company. Okay? They will compete. You know the Nash equilibrium anyway, right? So then the project is going to fail, right? So of course, teamwork is essential for the software development. As the result, conflict between the contribution of teamwork will be intensified. Okay, so in that case, you will see this is happening in real world because of the competition. Okay, so the bonus system actually encourages competition and then finally creating the conflict within the company, and the project will fail because of that, right? So the question is there any possible way to increase the trust among the team member, right? So how do we create a system that is actually controllable based on game theory? And we know a while ago we discussed game of trust, right? That it is possible to change the value of the system, rewarding system, to be this way. If they cooperate, they can actually get higher bonus. Okay? And if they compete, they actually get much lower bonus. Okay? So, how are we going to apply this? Okay? So, how do you reveal your expectation among your team members in detail, okay, so that they will perform? And how are you going to handle if your team member actually do not accomplish your expectation? Okay, how do you improve the trust among the team members? So this is the discussion that we can go along the way with this. And this is what I'm telling us, the right direction of control. Okay? This is a principle that we can say. If you want something, okay, so to get things that we want, right, then you need to set the evaluation of the performance in such a way so that when people behave in the direction that we want, they will get the reward, not the punishment. Okay? Similarly, if they don't behave in the direction that we want in our control, okay, they will get punishment, not reward. So this is simple principle, right? Of course, logical, right? So how are we going to do that? Is this example. Okay? Look, those who do violence get praised as heroes or defender of justice. Then you are setting the wrong direction of control, isn't it? Right? So those who cheat, for example, and tell lies will get praised as being smart. You remember when you are child, the children will get the story of Kancil and a crocodile, right? And Aladdin story, for example, or Alibaba story. So all of these are telling that, look, if you lie, you're smart. So basically, we are setting the wrong direction of control, right? So those who get rich out of corruption eventually become the appointed leader. So this is the wrong direction of control again, right? And if people say honestly, they get blamed as being rude or undiplomatic. Again, this is wrong direction of control. So if you know this is the wrong direction of control, then you can reverse this. Okay? So, okay, before that, can you state several examples of wrong direction of control that you know or you experience? Devi.
Wrong direction. The next one. Did I explain?
Joy. Cheating in the exam. Okay. So if you know cheating in the exam is not correct, and you get reward of a higher grade. So that is wrong direction of control. At one time, I was interviewing children, so elementary children in Japan. Okay, I asked them, oh, why don't you cheat? Just joking, yeah? Asking them, why don't you cheat? I was surprised because their answer is, oh, if I cheat, I will get higher grade, but my country lose. They said, oh, very cute. So I was surprised because as small as that, they have a system thinking already. I was, oh, that's very cute. I was shocked. Okay. So that is the right education. Okay. The right education that they have. Oh. Sleepy, you want to share something? What is the direction of control that you experience probably, or you know?
Corruption.
Corruption. So what happened to the corruption?
You get more money, but yeah, you will like
Yeah, you will make the society lose, right?
yeah.
Correct. So this is as simple as this. Look, wrong direction of control can be corrected by simply reversing, okay, the process. What does reverse mean? You just, if the reward is positive, then you just take it negative, or you can make it direction maximum minus that value. Okay, or you can stick to the main goal of control. So I give you example after this. So here, okay, remember, strong defense is the same as strong attack. Okay, so given the system, you can use a paranoid technique, huh, to list down all the possible cheating scenario. Okay, so you become paranoid, you suspecting, okay, how the others may cheat you. I'm teaching you to be paranoid, but look in the good way, okay? Including possible cooperation between any internal or external actors. Okay, then for each that scenario, paranoid scenario, now you create a robust reward or punishment system to prevent those cheating scenarios from happening. Okay, remember that even selfish people can trust each other better than to cheat each other. So you reverse the process. Okay, that's actually what I want you to do as a assignment. Okay, I posted there in Mentera. So here is an example. So in the current healthcare system, right, when we get sick, you need to pay the doctor, correct? You go to the hospital, you go to the doctor, oh, I'm sick. And then you pay the doctor because you are sick. So actually within the self-interest of the doctor that you get sick because they will get paid, right? But remember, the goal is actually to be healthy, right? So the better direction of control in healthcare system will be when you are healthy, you pay certain insurance. Okay, this is not happening, I know, but this is the reverse thinking. Okay, if you get sick, then the insurance must stop receiving the money from you and need to pay for your costs. Okay, then within the interest of the insurance to keep you healthy always, right? So we reverse the thinking. Okay, I give you another example. Say the security contract of a rich person. Okay, so say the current security contract of the rich person is if the security guard caught the criminal, okay, the security guard will get a reward. So look like normal, right? Okay, but using this contract, what will happen is the security guard can fake the catching of the criminal, okay, get more reward simply by cooperating with the criminal and the police. Okay, so the criminal will try to disturb the rich man, okay, get caught and send the police, who will release the criminal again, right? Oh, of course, this is just possibility of paranoid scenario. As the result of this security contract is the rich man will actually receive more petty crimes. Okay? They will get more disturbed. So then the question is how to reverse the direction of control to the right direction. Okay? So again, stick to the goal. What is the goal? The goal is to have no crimes, right? So in that case, okay, to experience no crime at all. So then you can create the security contract that actually prevent the crime. That means if no crimes was experienced by that rich man within certain time, okay, for 1 year, for example, then they get bonus, right? So by reversing the way of thinking, the process, and the contract, okay, then you can actually create a better experience. Is it clear or not? So the technique is first you create something like this. You create a system description. Okay, what is the current situation? Okay, and then using game theory, what you will do? You will think in the opponent point of view, right? What they will gain through cooperation. Paranoidly, you will do what is the bad scenario. Okay, 1, 2, 3 until end. So, and then what you will do? You will prevent. You will do a prevention by reversing that possible bad situation. Okay. As the result, you will create a trustable and robust reward punishment system. Okay, so what happened is why people don't do this because of the cultural problem, right? People usually, oh, I don't want to think bad about it. Okay, so yeah. So we can actually create a better family, better office, yeah, better company, better organization, better society, right? Using this technique, actually, yeah. We need to suspect. Suspect is not necessarily bad things. Yeah? You can. I don't agree that we always think positively. Okay, we need to use both positive and negative for our case. So in this case, you use the bad things, which is the bad scenario possibility, using paranoid discussion, right? And then you reverse the process. Okay, you reverse. If this happens, how are we going to prevent this? By reversing the direction of control. That means, okay, in that case, I will change the contract. Okay? I will change the reward. Okay? So this is not happening because of mostly cultural problem. Right? Many people tend to avoid paranoid discussion that, oh, I'm suspecting bad things may happen. Okay? But actually, by having the discussion on possible bad scenarios and the problem, it will make us well prepared, being ready, right, when things actually turn out sour. So this is the two assignment that I want you to do. Okay, one is a revenue sharing system. So suppose you own agricultural land. Okay, you want to create a revenue sharing system with the farmer. Okay. This is an old system anyway. But anyway, this is just a game so that you can practice. Okay, the farmer will pay for the work. Say the work is meaning preparing the land, planting the harvest, the seed, fertilizer, pesticide, and so on. And you pay for the land that you bought on loan, right? Of certain interest from the bank. So the goal is actually fair sharing, yeah? Maximizing the profit. Okay? In what way the farmer could potentially cheat you through cooperation with external factors? I put example there. Upon selling the product, for example, this honest farmer will be able to cooperate with the buyer, saying the price was low and so on. Okay? So, and then how are you going to prevent those cheating scenarios? Through modifying the contract. Okay? Create a system that is better for both of you. Okay? To create a win-win situation. Right? And second, the same assignment for next week is, suppose you own a shop or you own a factory, okay, and you want to delegate it to a team of workers. Okay? In what way the team of workers can cooperate within the team or with external actor to cheat you or to steal from you, right? And then how are you going to prevent those cheating scenarios? By modifying the delegation system and the contract, okay? Yeah. So that you will create a better reward punishment system that actually make a trustable system. Okay? Is this clear or not? the assignment. Exciting, right? Actually, this is very useful. If I notice, shop, many shop in Surabaya, for example, they are still handled directly by the owner, not delegated. Correct. Yeah? If I notice, I went to the Philippines, for example, you try to find the owner, is not there. They always delegate to other people, meaning they already create a system, delegation system. That means it is possible. Now, without delegation system, you cannot make branches. You cannot create branding also, right, for your shops and your company. So this is actually very important assignment, yeah, for your business, either now or the future. Okay. So as conclusion, okay, by assuming that human is actually self-interest, we can use game theory to create a better moral, okay, better society, than using a simple old dogmatic rule like the religion. Okay, and look, we can also use bad things for the good things. Nah? So paranoid thought is not always bad things. Okay, you suspect possible bad scenarios, and then what you need to do is combine this, okay, with reverse the direction of control to prevent those scenario from happening. Okay, so any comments, question?
Sir, for the assignment, do we need to like use the game theory that we have learned into that
Yeah,
question, or we just like
you just create a story, and then
okay.
the scenario. Okay,
Mm-hmm.
this is the possible scenario happening, and then this is how you prevent. On itself, that assignment is actually, if you look at the actual diagram a while ago, this is actually exactly game theory. If you look at the diagram, yeah. If you look at this diagram,
Mm-hmm.
right? So first you think in the opponent point of view,
Okay.
right? And then you reverse your thinking. Okay, what is this? This is exactly what you are doing in mass equilibrium, isn't it?
Mm.
Okay, so we try to apply game theory. Okay? You can put any numbers if you want, but it doesn't really matter whether you are talking qualitative or quantitative.
Okay.
Okay, so you don't put any numbers, that's fine. Okay, if you put numbers, that is also fine. So
Oh,
the point is you need to tell what is the possible bad scenario and how you prevent that. And then the next possible bad scenario and how you prevent that, and so on. Okay? As much as possible, as complete as possible. So that your system is actually going to be robust. Okay?
mm.
And once you make this, it's actually very important task for you. You can tell your parent. You can discuss with your parent, and I think they will appreciate this assignment as well. Okay.
Okay.
Okay. So I don't give assignment as game theory like computing, because the computation itself you already know very easy. I'm taking it as the philosophy, yeah, of the game theory, the principle of game theory, and we try to use this in our uh, real world application for business in this case, right? I think this is more useful. The way of your thinking is more useful than computation, because computation itself, computer can do, right? But if you can change the way of thinking, okay, suddenly you can apply in many ways in your life, isn't it? Okay. That is what the the real OR should be, right? It's not just to compute. You know, compute is computer can do, you know? But the way of thinking, okay, suddenly you start to realize, oh, OR is not just numbers and computation, but way of thinking change because of the OR. Okay, how useful it is. I'm trying to abstract the, the, the computation into principle, okay, and generalize it so that you can use it in your life. Okay, so we have 1 hour break and then we come back for the next game theory. Okay, so good afternoon again. This is our last part of the game theory. Okay, so basically just discussing on one type of game, it is coordination game that we discussed earlier. The slide name is network externality. You can check this in Netera. Okay. Yeah, in this lesson you will learn about what is called massive coordination game. So it has many n person, not just 2 agents, but many agents. N person games. So let's start with the simple coordination game like this. So you have 2 players, okay, A and B, Mr. Row and Mr. Column as usual. And Mr. Row have 2 strategies, A or B, and Mr. Column have 2 strategies, C or D. Okay. Now, if they coordinate, so if Mr. Row play A, okay, and Mr. Column plays C, both will get 1. Okay. But if they don't coordinate, okay, so that means Mr. Row play B and Mr. Column play D, okay, both will get 0. Okay. Otherwise, it's even worse. Or if they coordinate in AC or BD, so they get 1, 1 or 0, 0. But if they don't, they get even worse. It is -1 and -1. So, what is the Nash equilibrium here? First question is, what is the Nash equilibrium? By looking at it, I hope you are already expert in computing Nash equilibrium. Okay. Yes, AC and BD, right? Okay, so AC and BD. Now, what happens if you have million of players rather than just 2? Okay, so the same game, but instead of 2 players, now you have million of players. So this is called massive coordination games. So that means the player need to synchronize their action. Yeah. A while ago, I give example of traffic, 2 cars in the intersection, right? Based on this coordination game. So either they one stop and the other go, or both stop. Okay. Otherwise, it will create accident. Okay. So this kind of massive coordination game have another name. Okay. The another name is called network externalities. So this is based on the economic. Okay. So what is this? It says that the more people who has the product, the more valuable the product become. Okay. So, example, you will buy a phone only if your friend also buy a phone. Right? One phone by itself, nobody is using the phone. It's useless gadget. Unless someone else have phone, then you can communicate, then that phone is useful. The same thing with fax machine. If only you has fax machine in the world, this gadget is really useless. Okay, so only have at least 2 or 3 people have the same machine, then they can communicate, then become something useful, right? So network externalities is basically massive coordination games. Right? And why this is important? Because this is actually the dominant strategic consideration in many industries, in many business. So these are the questions. Okay? What are the example of network externalities? Right? If you know the examples, then you probably start to understand what is the meaning of this. And second, why this happen? Why these network externalities happen? Okay? And what are the characteristics of these network externalities? So understand deeper. And then how to win the massive coordination game. Yeah? So when I said massive coordination game is exactly the same as network externalities. Right? Okay, so these are one of the example. Your keyboard. Right? Can you see your keyboard have a QWERTY on it, right? So isn't that strange? Right? Why not ABC directly? Huh? Why QWERTY? Right? Right? So the more typewriter with QWERTY keyboard were sold, okay, the more people learn to type in that layout, and then the more successful this QWERTY machine. While the other alternative keyboard lost their business. So this phenomena is called lock-in. This is basically network externalities. Another example. In early days of motoring, if more than 50% of driver or countries decide to drive on the right side rather than on the left side of the road, then it will become norm of nearly 100% of road users. So why in this country, where do you, which side of the road do you drive? On the left. You drive on the left, right? In Indonesia, you drive on the left. That's why your driving is on the right. Right? Your driving seat is in the right. That means you drive on the left side of the road. Right? So the same as Britain, but in Europe it's the other way around. In US it's the other way around. Okay, so why the clock is rotating rotating clockwise? Okay. In early days of using circular clock, if more than 50% of the clock go what we now call clockwise rather than counterclockwise, this convention will become dominant, although the clock could just logically move to the left, right? So this is an example. The clock over Florence Cathedral moved counterclockwise and showed 24 hours. Okay? Soon after that year when the cathedral was built. And they standardized to 12 hours clockwise clock. Because majority of the clock has this feature. So in early days, this what we call as now clockwise is not a standard. Okay, that's the meaning. So this is again another example of network externalities. Now, into business, right? Network externalities caused by compatibility problem are the reason why most people buy Microsoft operating system. Okay, so more people who use the same type of operating system as you do, the more software there will be for you to use. So the customer play coordination game for each other, where most people want to use the same kind of computer as everyone else does. Okay. So now let's between Apple and Microsoft, and we have two players, player one and player two. So what is the NAS equilibrium? Right. So Apple, Microsoft, is the NAS equilibrium, right? So, correct. So, of course, Pareto optimal is Apple, right? So this is probably about quality, but why Windows is dominant over Apple, right? So what happened is not because of the quality, but is more on network externalities. Okay? So market dominance is not just about quality. It's more about network externalities. So the technological challenge achieving backward compatibility give the competitor another advantage over Microsoft. So actually, to preserve backward compatibility is actually very big challenge for the Microsoft engineers, right? Okay, so but it's a policy of Microsoft to create a backward compatibility. Why? Because they know this is creating network externalities. What happened is around 2000, year 2000, Microsoft changed from Bill Gates to Palmer, and then they introduced PhoebeNet, which is not fully compatible with PhoebeSix under Bill Gates, and basically because of lack of this backward compatibility, Microsoft killed the Visual Basic language, okay, which now you use in Excel as the VBA. Okay. So backward compatibility is very important to create the network externalities. Yeah? The same with Microsoft Word. Yeah? Microsoft also received massive network externality profit from Microsoft Word. Okay? It is easier to share word processing file if everyone uses the same program. Right? That's why to attack these network externalities, what Google is doing is giving you free program instead of paying, okay, Microsoft Word. And because of that, Microsoft now giving Word also for free, right? So that is a war about word processing program between several businesses because they know this is a massive network externalities. Okay. So English right now remain popular because it's widely used. Even though if you calculate the total, Chinese probably have more people to use, but English is now become lingua franca. Okay, so it is massive coordination game. So the educated citizens of the world have decided to learn English, yeah, either as first or second language. So the same with computer programming language. Right? Why only a few programming languages actually become so popular, like Python, C++, Java, and so on. Right? So there are hundreds of programming languages, but only a few are popular. Right? So money. Okay? Our use of money is based on massive coordination games. Do you realize that? Okay. So, for example, you have money, dollar, for example, it's just piece of pretty paper that are useful because people value them. You cannot eat money, you cannot wear money, okay? You cannot watch money as a movie. So, if the entire human race, say, you become extinct, for example, because of certain things, okay, money will no longer hold any value to you. Okay, rice will. Okay. So money has value because other people want it. So this is massive coordination game. That's why the creator of Bitcoins understood this. So money is just a massive coordination game. Yeah? Because so many people want money, then it is useful to have it. Yeah? Because you can trade the money for goods and services. Okay? The same thing with lottery. When many people play lottery, then they become more excited. Okay? Attract more players. So if only a few players, it will not become attractive. Sport game, right? The same. What is the most popular sport game in here? Is it soccer? Right? Probably. So in the Philippines, probably the most popular game is actually basketball. Or maybe here, badminton is also popular, right? So this is sporting fun in a country effectively play a massive coordination game, right? Where they all choose popular sport and then everyone else interest go along. So if most people in your country watch soccer, then maybe you should also do the same, right? So give me any example, example of each of you. Can you give me example of network externality system that you know? At least one. Yeah, cryptocurrency. Okay. Livy, give any one example.
Wait, network externality.
Hmm?
How about
What things that many people use? What the social media using?
the the
What social media are you using?
uh uh several social media like WhatsApp and then Instagram.
Okay, Instagram, WhatsApp, right? So
Yeah.
you're using that.
Because many people use it, so
Yeah,
I
because many
think
people use it, right? So you use it because many people use it. So that is exactly the example of network externality, right? If nobody use, you will not use. Correct?
yeah.
Yeah. Okay. So in the early days of Facebook, for example, okay, they have a lot of no profit at all. Yeah? They basically no revenue, right? But they know this is a massive coordination game. So what they do is they keep growing, okay, the number of users rather than getting the money. So that is their strategy. Yeah? Their strategy in business is to create more users rather than to create money first. Money will come later. That's what they say. And now that is proven to be true, right? So the next question now, okay, those are the examples, right? Why is it happen? Why the clock go clockwise? Why people in many nations drive on the right side? Why people try to use QWERTY keyboard layout, even though this is inefficient? Why Microsoft Windows or Intel processor dominate the market for PC? Why do we use English? Yeah? And probably one of the question is why the rich get richer and the poor get poorer. These are all the same question. You know? Yeah? So people will ask, oh, the gap, the economic gap between the rich and the poor. Right? This is all example of network externalities. what do these questions have to do with each other? Yeah, they all pointing to the same phenomena. Okay. Another name of network externalities or massive coordination game is path dependent. Okay, I will show you why this become path dependent or lock in. So these four jargon all the same thing. Eh? Okay, so path dependent behavior is a pattern over time. So this is actually in system dynamics. Okay, it's a pattern of behavior in which the ultimate equilibrium depends on the initial condition and random shock. So this is a difference equation. Okay. Okay. True. This is different. I will show you in a moment how the difference equation works. Okay. This is actually difference equation, and you can see the connection between difference equation and game theory. Okay. So the path dependent system, yeah, small unpredictable event in early history of the system, okay, can decisively determine the ultimate fate. Okay, so the term is actually lock in. Yeah? Even when all paths are initially equally attractive, okay, and then suddenly the symmetric is broken by the microscopic noise. It's purely random chance. Okay, that noise is random chance and external propagation. So what happened here is there is a positive feedback loop, yeah, that amplify these small initial differences until it reaches macroscopic significance. Once the dominant design or the standard has emerged, then the cost of switching suddenly become prohibitive. Okay, so this equilibrium is self-enforcing. So that system becomes locked in. That is how the phenomena happening. So what is the cause? Okay, the cause is first there is a dominant positive feedback. Okay, and there is locally unstable equilibrium, and it will be perturbed by random noise to create a lock-in. So I already explained this stable equilibrium and unstable equilibrium. So I just pass this. So the process is very simple. This is called Polya process. Polya is one of the scientists. So he said, look, I can create this lock-in process as a path-dependent process. Okay, imagine you have a jar. Okay, and then you will put small black and white stone, right? And then the color of the stone that you add every time is by chance. Yeah. For example, this time you will put black. Next time you will put black again or white. It's just random, pure random. Okay. So the probability of selecting the black stone is actually equal, yeah, to the proportion of the black stone that already in the jar. That is the key. Yeah. So this is the key assumption that make the system create path dependent. Yeah. The probability of selecting a certain stack of stone is equal to the proportion that is already inside. Okay. So Polya system has two feedback loops. Yeah? One is positive feedback loop and the other one is negative feedback loop. So the positive feedback loop said the greater the number of black stone, the greater the chance of adding another black stone. Okay, that is to make the growth of the black stone. The second is the negative feedback loop. Yeah? At the same time, the greater number of stone produce smaller impact for any black stone added to the jar on the proportion of the Blackstone. Okay, so this is the negative feedback loop to stabilize itself. Right, so this is the system. I call this a stock flow diagram. Okay, if you look at this, there are two levels. This is the level. Yeah, this is the state level, and these are the rate. So there is an input, and this is the input to the Blackstone. This is the input to the Whitestone, and there is a random draw to that rate. Yeah, random draw to that rate. So this represents the symbol of constant. Okay, and this is another proportion. Just we want to know the proportion of Blackstone and the proportion of Whitestone. So the difference equation is something like this. Okay, so initially you have a white Blackstone 1, and then this is the difference equation. It's just accumulation, and the same thing here. Okay, initially you have Whitestone of 1, and then this is the difference equation that you accumulate in this level. And this is the adding of the Blackstone per period. Okay, that depends on random draw. Right? If the random draw is less than the proportion of that, say this is for the Blackstone, okay, then select that proportion of Blackstone. Otherwise, 0. Okay, and then you multiply by the number of stone added per period. So with that, we can start to see the path-dependent system. Yeah? That the result is just this. Yeah? Over time, yeah, the proportion of Blackstone can go up or go down. Okay? That purely random. Yeah? Can go up to 1 or go down to 0. So it's purely random. Okay. So what happened to in the part, for example, is going up above 0.5 and then suddenly go. Initially 0.5 and then suddenly it will go down to 0. So this is what the system look like. Okay. So the popularity of any product, okay, will provide a lesson for the firm marketing goods with the network externality. So the key to success results from getting many people to coordinate to buy your product or to use your product, right? So consequently, marketing goods with network externality actually based on perception. That perception will become reality. So you influence the perception of people that people already using. Many people already using it. So if your new product has become network externalities, okay, because many people think it will become popular, then there is good chance that it actually become popular. Do you get it? So you influence the public perception, and then that perception become reality. And so to win this massive coordination game, okay, of course this is a winner take all, right? So in that case, it's very important, yeah, if you want to win, it's very important to be perceived as popular. So this is like you are using faith. Yeah, that is it. And then you keep telling your faith, and then eventually your faith become reality. Yeah? So when playing a massive coordination game, it's a sound strategy to buy early popularity by selling your product at loss. Sometimes many startups doing this strategy, right? They want to win the competition, to be perceived as popular, okay? And then they are selling their product at loss. Yeah. So a product stay popular because it is popular, right? So with all coordination games, once everyone have decided on a strategy, everyone benefit for continuing to play along, right? So in that case, people will use the product with network externalities because they like them, because they think other people will use them. So it's very important to understand network externalities so that you can have the product that's actually popular. Okay, up to here, is there any comment, question? Give me feedback what you just learned. Any of you? What is that? What is network externality in your opinion? How? Promo. Mm-hmm. Okay, so you create a perception, right? That this is actually useful and many people already use. Then eventually people will use. So that is the strategy based on this network externalities. Yeah, Livy, you want to say something?
Yeah, so basically this network externality is useful if many people use it, right?
Correct.
Yeah.
You know, there are certain product is useful because many people use it. Then the question is, uh, okay, I know that, right? So now I have a product. How I will make this useful so that many people use it, right? So one strategy is to create a perception. It's not real, okay? But you are telling not the truth, huh? Okay? You're just telling the perception that this is already used by many people. Okay? And eventually, even though in the beginning this is not the truth, it will become the truth. That's the funny part there. Okay. So even though in the beginning this is just faith, okay, eventually it becomes true. So that is the characteristic in network externalities. So your lie become true. Okay. So interesting. Okay. So with that, I want to stop discussing more about game theory. There are actually still many if you want, but I think we should stop here and then go to the next lesson. Yeah? Otherwise, the whole class will become just game theory. Yeah. So we have discussed in the beginning. We have discussed about decision, right? So we discussed decision under uncertainty, where you don't have any probability. Okay, and then we talk about decision under risk, where you have probability. Okay, and then we talk about decision under utility. So the most important there is uh, the notion, yeah, the ability to understand what is utility. Okay, so the whole economic theory is basically based on utility. Okay, so and once you understand utility, we start to go into group decision. You remember, including veto power and politics. And then the last part is the game theory that we discussed. Okay, we discussed at least two parts. Okay, one is called zero-sum game, right? The other one is non-zero-sum game. So network externalities is basically non-zero-sum games, yeah? Including the system control available. Okay, so I hope this is useful. So the next topic will be on queuing theory. So I think one of you, I think Joy have a project in queuing theory. So yeah, let's go to queuing theory then. Okay, I'll close this. And yes, go to the rest. So, is there any question about the game theory or decision theory that you have learned?
For now, it's clear.
It's clear. So, is there anything that you think you can use in your life from this lesson?
Of course, because I will like try to think what others think, so I can make the decision better.
You can start to think of other things, right? That is very less.
The probability.
Yeah.
Yeah.
Right. So our next discussion is about queuing.
Is this queuing theory can be applied in the traffic jams problem?
Exactly. So actually, queuing is the same as traffic jam.
Oh.
Okay, that's the exact thing. Okay, so not just can be applied. This is exactly the same. Okay, when you see traffic, okay, jam, that is exactly queuing, right? In this lesson, I want to abstract, okay, not just the queuing theory. Of course, I will discuss the computation, optimization, but I want you to understand better than that, so that you can apply the queuing theory for any problem, not just for things that you see as queuing. In fact, it's a way of thinking that I want to emphasize here. Okay, and based on this queuing theory, you will solve many other problems as well. Okay, so let's start with the simple things first. So I don't know if this is exists in the. Can you see my screen?
Yeah.
Okay, so this is a queuing problem. Okay, yeah. I hope by this lesson you will understand the input and output of queuing and the role of theory and distinguish different type of queuing. Right. So, okay, what is queuing? You know what is queuing? I'm having a hard time in Indonesia to explain what is queuing because it seems like there is no queue. Right. Actually, most people will think queuing is a waiting line, right? So something like this. Yeah. So traditional queuing is a waiting line. So traffic congestion is also queuing. Yeah. So this is the police dog in China queuing for lunch. So even the dog can queue. You see, yeah, you create a waiting line. So the same thing with this iguana queuing for the food. Right? So what's the difference between the left side and the right side here? This queue is creating a waiting line. Okay, this is also queuing, so this is called bulk queue. Okay? So, okay, they are queuing for the food, right? So it's not creating a waiting line, but they are still queuing for the service, which is the food here. Okay, so I call this bulk queue. Okay, where you can see they are waiting for the service. Okay, but not creating a waiting line. So waiting line, you create a line that they queue. Okay? But the two of them are queued. Can you see that? So congestion, say this is a gate, these are ships, okay, passing through the gate. Okay? Oh, thousands of them, right? You can see the arc in it. Can you see the arc? I will start to draw that. There is an arc, okay, of the queue. Yeah? And this happen not only for the ship, okay, also for pedestrian. Okay? When you have a bulk queue, this is called bulk queue, right? So there is a service of this gate. Okay? The service is to serve the ship to pass on itself. So, and there is a phenomena of this arc phenomena, yeah, which also happen that when we do a pedestrian, human will also create similar phenomena. Okay, so in order to make a waiting line, okay, or certain discipline with this first in, first out, right? FIFO. So then you start to enforce the discipline. Okay, so this is an example. A policeman is using stick, okay, in India, so that they will behave to create a waiting line rather than bulk queue. Okay. And of course, queuing is also in transportation. You see, this is just in the top of Ateneo campus in front. So, yeah, this congestion here, okay, is representing queuing. Yeah, the same thing with people who want to enter the MRT, right? Okay, the train is also queuing. And this is the story in Singapore, right? They avoid queuing because at that time iPhone 7 was hot product, yeah, at that time. So and then they don't want to take long line, so then they went to the airport, yeah, to buy the iPhone without flying. So apparently in Singapore that is not allowed. So they go to jail just because they buy an iPhone 7. This has become news, because it's strange law. Okay, so question sometimes people will ask, is queuing good or bad? Okay, so, well, I will say for whom, right? So when iPad 2 was hit in Japan, yeah, people queuing very long time, yeah, and they are very happy to buy that iPad, right? So of course that is become network externalities. No? So people think that this is popular, so the more people think this is popular, the more people will buy. The same thing if you have a restaurant, okay, and then people willing to queue outside, and the longer the queue, right, then it's very, very good for your business. In fact, if you want to have your shop, okay, popular, probably you will make the service very slow so that people will queue, and then people will start to think that maybe this is good, right? So, of course, in general, that is not really true, okay? But that is only perception. So queuing is actually pervasive phenomenon. Okay, so in the bank you will queue, right? In the traffic itself you will queue. In hospital you queue, right? In government offices, supermarket, well, oh, uh, in fact, the queuing itself is not just for human. Okay, so the music will play in the list. Okay, music box. That is actual queuing. Okay, you create a to-do list. Okay, that list itself is a queuing, right? To be checked that you are already doing. Okay, in the amusement park, like Disneyland. So you want to ride, then you queue. Okay? So uh, if you want to enroll every semester or every year, okay, in the university, you do enrollment, that means also queuing. The document in the office need to be signed by your boss. That is also queuing. It's not you who queue, it's the document that queue. Okay? The files or the product queuing for the machine to be served. Right? So if you look at this, you start to see queuing is not just for human, for any kind of system. Okay, so my question, can you give at least one example? Not mentioned here of any queuing.
Our assignment.
Oh, tell me, what is your assignment mean? Oh, the assignment is queuing to be solved
Yeah, to be.
because too many assignments. Very good example. Okay, Joy, you have any other example? Yeah. So, any example? Okay. So airlines, okay, the airplane want to land,
Mhm.
they need to queue for the runway. That costs a lot. The same with the ship want to enter the port, they need to
Mhm.
queue, the berth, right? So so these are the problem in queuing. Yeah? One is too many server. Why is problem? Oh, it gives you rapid service, isn't it? But it creates idle workers, okay, underutilized equipment. So it costs a lot. Okay, if you say, oh, it's a traffic congestion, right? Traffic jam. So why don't we build more wider road? Okay? That will create underutilization. Okay. So another is if too little server, oh, become long queue, right? The customer become impatient. They will go to other shop or other business, not to you, right? So, and if it is in the factory, the congested floor, shop floor, okay, so become messy. So you don't want too many servers, you don't want too little server, isn't it? You want balance, right? You want to optimize. You see that, right? So why queuing is a problem? So economic loss. Okay? If the customer kept waiting, so for example, the airplane waiting for to land, it will consume a lot of fuel while waiting, right? That cost. The same with food product, okay? Maybe spoil. It will take too long to reach the customer, okay? Or loss of customer is loss of opportunity for doing business. So these are the possible loss of economy because of queuing, right? So I usually give this as assignment. So you already complained about too many assignments, so I will not give you. Okay, so why we learn about queuing theory? Yeah. First is to predict the queue length and waiting time. Okay, so this is basically a tool for optimization. You don't want too much, you don't want too little, so you want to optimize, right? And of course, you want to create efficient, okay, cost-effective workflow of your business. So you want to reduce the opportunity loss, and you want to provide good service. Okay, for traffic flow, okay, you want to minimize the delay and traffic congestion. So these are example of benefit of learning in theory. Okay. Look, if you look at queuing, okay, queuing, the management of queuing system is usually interested because of this. Yeah? First is the evaluation of the system performance. So you have a system, you want to evaluate that system, right? So you want to know my current situation, my current system is good or not. Second, you want to predict, okay? You want to predict the future performance of your system, okay? And the third one is you want to compare, okay? The performance of your current system with the alternative, right? So you want to compare your proposed system with the current existing system that you have, okay? So if you create a queuing project, this is what you need to do. Three things. Yeah? To evaluate the current situation, to predict, and then to propose by comparing your proposal with the existing one. Of course, the hypothesis is your proposed system must be better, right? Otherwise, why you propose? Okay, so here are example of queuing problem. So we want to know how many additional servers must be employed. For example, to reduce the proportion of customer that have to wait longer than 1 minute or less than 10%. So if we introduce, say, for example, priority to the first class customer, what will be the effect to waiting time? How much should the waiting room be enlarged to reduce the proportion of customer turn away to, say, certain numbers, less than 1 in 10? How much improvement of service can be accomplished if the length of service time is shortened from 5 minutes to 3 minutes? So based on this queuing model, okay, then you can actually answer all of these questions. You can read more of these question problems. I have put a lot of example of problem. So, okay, so to solve queuing problem, there are many ways. Okay? One is to do direct observation, and then you calculate the system statistic. Second is to do what is called a queuing theory. This is what we discuss in this class. And then you can also use simulation. Okay, and I propose, I think 2012, 10 years ago. So I propose what is called queuing rule of thumb. So I will discuss next meeting about this. So any queuing system consists of, because it's a system, so consists of input and output, right? So the input consists of two, okay? Basically the customer and the service. Now, what I want to tell you is, look, the whole economy is actually a queuing system. Yeah? Okay. So from the factory, you go to the distribution center, right? And then to go to the warehouse, to go to retail, and finally to go to the customer. All of these are a queuing system. Can you see? So queuing is more than just one small system that you think. Okay? In fact, this is very important. the customer here represents the demand side. Okay, you can say about the arrival process, okay, the distribution pattern of this and so on. And then you need to know whether the population is finite or not infinite. Yeah? Second part of the input is the supply side. So I said the supply side is the service. Okay, so you need to know the service process, the configuration, the waiting capacity, and the discipline, yeah, the service discipline. Okay, the output of a queuing system, any queuing system, let's call this MOE. Yeah? What is this? Measurement of effectiveness, or basically performance measure of the system. Yeah. So now, okay, I'm trying to abstract the queuing theory. Okay, so we're generalizing the queuing problem, not just the queuing that you see as, waiting line, but the whole economy. Okay, actually a queuing problem. Okay, based on demand and supply. So logistic distribution system is a queuing problem. Right? So each part is just one queuing system and connected in series or parallel with other parts. So if you want to solve the economic, you can use a queuing theory. Okay. So this is my website. Okay. So you can visit. I explain everything there, including the queuing calculator is there. Okay. Some professor in MIT also using this. Okay, so they report to me that they are using this. So basically, this is useful for anybody, not just you. Okay, so that's the first part of the queuing problem. Just beginning, introduction. So next meeting is the meeting. So I will start with the basic queuing, okay, with the definition and so on. So up to here, is there any question? Is there any question that you want to ask or any discussion?
Sir, I have one question.
Cool.
For example, if we order food or like want to order a go-kart, is that counted as
That
a
is a
queuing?
queuing problem, yes.
Oh,
That is a queuing problem. Okay, how to make things more efficient.
mm,
Yeah. Someone created a Wikipedia of queuing rule of thumb. Okay, based on my work. So I don't know if they mentioned me, but at the same time you can check. Yeah. Queuing rule of thumb.
mm,
So let's start from. So here, this is what I want to share a little bit before we close. Okay. This is the detailed traditional of queuing system. Traditional queuing. Okay. In traditional queuing, the customer arrive in the queuing system, and then they are waiting, right, in the waiting line to be served. And then, what is the process? The customer is being served, right? And then they go out of the system. So look at the detail, okay, when the customer is being served. Okay, so say you are in McDonald's, for example, yeah, the customer will transfer information, the order, for example, yeah, the item to be purchased, the ID, probably, to the server, right? And next, the server will input that customer data using scanner, typing, and so on, okay, cash register, and then the server will do the order processing, maybe preparing the food, cashier get the money and so on. And then there's a transfer of material or the information from the server to the customer. So, for example, the receipt, the change, the food itself, right? Or the document, right? So this is the traditional queuing system. Okay. So what happened is I'm trying to generalizing, okay, of queuing system into these two. Okay. Basically, where is my definition of queuing? No, I did not put it here. Okay. So queuing theory happened started in 1917 by Erlang, yeah, for the telephone industry, yeah, telephone system. So that's why you will see a lot of model from Erlang, okay, and there is a Erlang distribution also. Right? So this is originally it's a body of knowledge dealing with waiting line. Yeah? So how are we going to abstract this queuing so that you can use for any system? That is the challenge. Okay, can you start to think about it, and then we will discuss next meeting. Okay, I already gave you several clues. Okay, so thank you for today. See you next week.
Okay, thank you, sir. See you.